So my name's Christian Bitzas. I'm a computer engineering student here at the University of Wyoming, and I was part of a team that worked on GPS radio occultation with the 2020 LIFT project under the Wyoming NASA Space Grant Consortium. So what I'm going to cover in this presentation is the background of the project, what radio occultation is, the payload we sent up on a balloon, our launch and results, and then a tiny bit about our STEM outreach and teaching that we did with this project. So a quick introduction is, again, this is a radio occultation project done under LIFT. And LIFT is the learning to integrate fundamentals through teaching. And this is something that allows undergraduate students, such as myself, to pursue undergraduate research on a specific topic and project. So what's cool about LIFT is it's multidisciplinary. So it's a few teams. Each team has a few students, each with different majors. So in my team, we had a science major, engineering major, and a education major. So, and then we each focus on our specialties and work together to do undergraduate research and present our research to a partnered classroom. So first of all, what is radio occultation? So radio occultation is a process of remotely determining like atmospheric properties such as temperature, humidity, and pressure. So how does this work? So how it works is you have your GNSS satellite, which in this diagram on the right, you'll have it right here. And then what happens is this GNSS satellite spits out signals that your phone and your car can collect and determine its location. But this is used by a low Earth orbiting satellite, which uses that signal and it compares it to when the signal does not go through an atmosphere, and then when it does go through an atmosphere, and then it compares those signals. So as you can see, the low Earth orbiting satellite kind of occultates. It goes either rise occultates or fall occultates over the horizon. And as if in this case, it's falling. So you have a case where you get a straight signal and then another case where it goes through the atmosphere. And as it goes through the atmosphere, it kind of bounces around, it changes. You can look at that comparison and figure out the atmospheric properties such as temperature and humidity. So we wanted to put our own little spin on it. So we thought, why not use a radio sim balloon? And we thought about this because it's a lot cheaper than a low Earth orbiting satellite, and you can do location-specific observations. It's not well researched. There's a couple papers on radio occultation using a balloon, and most of those are written by a professor named Dr. Haas, who works at Scripps University. And she does a lot about this. I actually had a Zoom call with her at the beginning of this project regarding this, and she helped me pick the hardware, and she gave me a lot of tips for radio occultation. So what we sent up on the balloon is we sent up something that looked just like this. This is a phone box that had all of our hardware inside of it. On the outside, we had our GPS antenna on top, and then we had our thermocouple sticking out the bottom. And then inside of this payload, we had our GPS receiver, and then we had a omnidirectional GPS antenna. So that means the antenna was able to collect GPS signals from all directions. And then we also had a Raspberry Pi in there, and then connected to the Raspberry Pi, we had a BME 680, which collected digital temperature and humidity, air quality, and a few other things. And then we also had our Type T thermocouple over here. So this is just an analog wire that uses resistance to determine temperature. And then we also had our battery pack. And then this is what it looked like on the inside of the payload. On the inside, we had all of our sensors, our Raspberry Pi. So usually our Raspberry Pi would be mounted on the side, like down here. And then this is our GPS receiver, which would go down here in the middle. And then on top, we'd put the lid on, and then our omnidirectional antenna, the wire would go through and connect to the GPS receiver. So we use this on a launch in Buffalo, Wyoming, on October 28th with the Clear Creek Middle School. So this is our partnered middle school that we kind of taught, and we'll talk about that later, but this was our main launch. We did a couple test launch, but this was our main one. But for a main launch, unfortunately, the payload went offline about 70,000 feet, but we were able to get some good data. So if you look at this image on the right, you can see this little green trail. That is the flight path of our balloon. And you can kind of see where it went offline. It kind of spiked down. That's probably because of battery readings due to low power. So that's kind of what the trail looked like for the balloon. And then a couple quick notes about this is we took one sample a second at 1 hertz. And This caused some issues in the future with post-processing, which we'll talk about as well. But yeah, so also with this payload, with the Septentrio Mosaic GPS receiver, we recorded a few GPS signal bands. We recorded L1 and a couple L2 bands, and we did record the L5 band, but we didn't use it in post-processing. And we used these L bands because we only recorded through the GPS constellation. There's a bunch of other constellations such as GLONASS, NAVIG, stuff like that. So we just focus on the United States GPS constellation, their GPS system. So what data did we collect? And so when you do radio occultation, you pick a specific satellite and one that either rises or falls over the horizon. So in our case, in our data, we saw that G08, which is also known as USA 262, Navstar 74, and there's a couple other names for it. We saw that it was occultating over the horizon. And you can see it right here on the sky plot on the left. And you can see how it was about 333 degrees or 330 degrees from north. And then on the right here, you can see a diagram with it in relation to Earth. So you can see how it was at about 20,000 kilometers in altitude. And you can see how it's about the 330 degrees north as well from where we were, which was Buffalo, Wyoming. And then from this, the data we collected on the balloon itself, we collected temperature, humidity, pressure, and air quality, which we fed into a program to help estimate and help predict the atmospheric properties such as temperature. But then in terms of the GPS data, which this is only for G08, that satellite, a specific GNSS satellite, we collected the carrier to noise ratio, the phase of Doppler shift, and the phase Doppler rate for that satellite. And on the right here, you see the Doppler rate, which is the rate at which the Doppler effect was happening. And we won't really talk too much about that because of time, but we also down here have the carrier to noise ratio, which this is like the strength of the signal. So the higher this is, the higher carrier signal you have compared to the noise. So the higher it is, the better. And then, yeah, so with all that data, we threw it into a application called ROPP, which stands for Radio Occultation Processing Package. This was a software made by ROMSAF, and they created this package to process radio occultation data between satellites, which is kind of an issue for us because our balloon was so slow moving and we relied on the GNSS satellite occultating and not the low Earth orbiting satellite, which in our case is a balloon. So because of this, we did have errors with our processing. And because of this, we are not really able to show real results as of right now, but the expected results, this is a simulation of what it would look like. So this is kind of what you would see if we were able to process our data. So you would see a sort of chart. You could plot it. You plot dry temperature and versus the refraction height, and you can kind of see how at different heights the temperature is affected in the atmosphere. So this is all done remotely, and yeah. So that's it with that. To get our data to be processed by this, we had to throw into a bunch of Python scripts and do satellite estimation. So there's that. Now, finally, we have our teaching and STEM outreach. So with LIFT, you are partnered with a classroom in Wyoming. We were partnered with a classroom at Clear Creek Middle School in Buffalo, Wyoming. So throughout the semester, we did experiments with them. We did classroom visits, well, through Google Meets because of COVID-19. We weren't able to go visit the classroom, but we were able to go there for our balloon launch. So we did have an education major on our team, which took care of a lot of the teaching education side of this project. So there's that. Here's a few pictures of our launch on October 28th. And that pretty much wraps up the education part of this project and this project in general. So yeah, are there any questions?
I had a question about you. Awesome. I know you still have the payload with you, right? Or you have it, or Kevin has, or somebody has it.
I do.
So are you still trying to get it to work, or has it just been sitting off?
So for the semester, it's kind of just been sitting there. Okay. But I'm waiting on because Dr. Kilty wants to try something using, it's called a GeoID, I believe. So it takes an image of Earth, of a top-down view of Earth, and then it kind of detects instability indexes for weather. And then he wants to use that and then use our GPS receiver to like find temperature through that. So I'm waiting on Dr. Kilty to make inverse functions for it. So hopefully this summer I have to reach out to him and see what he wants to do with that. But
yeah, this was a really ambitious project, but I'm glad that you found it to be really, really helpful and useful in your own education, because it's clear that you really enjoyed delving into all the details here and learning about this complicated process. So I think that turned out pretty well overall, I think, even though the data has been iffy.
yeah. And I have to agree. This project was by far really helpful to me. And I learned so much through it. I think this project is the most I've learned in college, probably. So,
Wow.
yeah. And it was fun too. And I learned a lot about all like satellites, GPS. I didn't really know much about that before. So I learned a lot about that. And then I feel like there is still a possibility of processing that data. So hopefully,
Mm-hmm.
but it was definitely a fun project.
If you had to do it again, what would you do differently?
What I do differently? I would like the same project or radio.
Yeah.
I would try and look earlier for a way to process the data because or I guess find a simpler way to process the data, like might not be as specific but find like a general atmospheric reading, because right now all the data we collected was pretty good, but it's just the processing part of it that was really really complicated, so probably focus more on that and then maybe use a bigger antenna, stuff like that, because I guess the more accurate readings you get, the easier it is to process. And then look at how low Earth orbiting satellites, how they differ from the balloon. Because like if we can simulate a low Earth orbiting satellite and its movement with the balloon, like kind of fake it, it would also be easier to process too. So that's all stuff too, if I was ever to do it again or look back into it, that's what I would probably do. So yeah.
You had mentioned the 1 hertz data that you collected and that was problematic.
Yeah.
Was that because at every 1 second the balloon is moving way too slow compared to a satellite? Is that what it has to do with?
Mm-hmm. That is 100% what it is. So when you use GPS radio occultation, you use a low Earth orbiting satellite, it's moving super fast. And even though it's moving super fast, you're taking hundreds or thousands of samples every second. So our balloon, we took 1 sample every second, but it's still moving way too slow for it to simulate the speed of a satellite.
Mm-hmm.
And also the issue was because of how slow the balloon was, we were relying on the GNSS satellite, the high one, to occultate, when usually the low Earth orbiting satellite would be the one occultating. So that was another issue with that.
Yeah, I guess you need some big differences in position in order for this to really be robust, right?
Mm-hmm. Yep.
Yeah. Well, it's the best we can do with what we got, right?
Yeah. But I feel like it still went pretty well, even though we weren't able to fully process the data.
Yeah. All right. Well, thanks again, Christian. Good job. And look forward to hearing what you end up doing with this stuff in the future, if you make any more progress and all that.
Hopefully we do. And thanks for having me.
You bet.